So that's the first thing. And color. Fluorine is a gas. It's a pale yellow gas. Chlorine is a greenish yellow gas, and bromine is a orange brown or a red brown liquid. And this one is a blue black solid or a purple vapor. You can also add another color that if it's in solution. In solution, iodine is a yellow. It forms a yellow solution if it dissolves. So I2 aqueous, that is yellow solution. So that is yellow solution. And then you have then the other things are that the melting and boiling points increase as temporary dipole induced dipoles increase due to larger size. Color gets darker. So they all have van der Waals forces. For example, if you have a fluorine molecule and you have another fluorine molecule, they have temporary dipole induced dipoles. For random reasons, this side could become negative, this side could become partial positive. It could attract electrons from the other molecule, and the electrons can be pulled, or a dipole could be induced on this molecule because of the first dipole. So that's temporary dipole induced dipoles, and they depend on the size of the molecule. The larger the size, the greater would be the melting and boiling point. So you have van der Waals forces. And the size of the van der Waals forces, it keeps on increasing, and the color becomes darker and darker. The next part is the bond strength. The bond strength is that usually what happens is that smaller atoms, they make stronger bonds, but fluorine is an exception. And why is fluorine an exception? It's because of the lone pairs. Like if I draw the molecule of fluorine, the problem with the fluorine molecule is that it's so small and it has so many lone pairs. Now fluorine likes to really attract electrons. So here's a fluorine molecule, and here's another fluorine molecule. And this molecule is going to be attracted or forming a covalent bond with this other fluorine molecule. Now the problem would be that fluorine has so many spare electrons that the electrons, they start repelling each other. So because of the mutual repulsion, the lone pair repulsion, that kind of weakens bond, and it's very hard for the fluorine molecules to actually stay together. They would be attracting each other's electrons, but the lone pairs would be repelling each other so much that it's going to be. And fluorine has it's a small atom. The lone pairs are very concentrated. They have a very high charge density, which is why the repulsion is even greater as well. So is this point clear? Guys, is this clear? Mohammed, Ibrar, is this clear?
Yes.
Yes, sir.
Okay, so just remember, fluorine is an exception. Otherwise, smaller atoms, they usually form stronger bonds. Now, that's not an issue when you talk about the bond strength of hydrogen halides. That doesn't seem to be an issue there. Smaller atoms, they form stronger bonds, and bigger atoms, they form weaker bonds. Why is that not an issue there? Because if you look at an H atom and you have a fluorine atom on the other side, and they're going to overlap and they're going to start forming a bond. Now the issue over here is that fluorine still has lone pairs, but H has no lone pairs. So I mean, there is no point of repulsion because H is completely empty. It had one electron. It's sharing that one electron with the fluorine, but there would be no mutual repulsion because there are the rest of the hydrogen atom is completely empty apart from this. So H has no lone pairs, hence no lone pair repulsion. So pretty much the trend follows. Bigger atoms are weaker, smaller atoms are stronger, and uh, and HI is kind of very weak. It decomposes very easily. And then we're going to talk about the boiling points of hydrogen halides. Boiling points are that HF has very high boiling points, and the reason is that it's capable of forming hydrogen bonds because of the very strong charge density of the lone pairs, and because of the highly polar nature of the bond, because fluorine is one of the most electronegative elements. The two HF molecules are going to attract each other they're going to attract each other very, very strongly. Okay, so there's going to be a very strong mutual attraction between the two molecules. Is this clear?
Yes.
Yes, sir.
And then there's this other issue you get asked a lot about this. It's about the trends. Let me use the other pen just a second. Now the other thing is that you're going to be asked very frequently is about the trends of HCl, HBr, and HI. What are they doing, and how are they melting and boiling points varying? So HCl, HBr, and HI. Now in this case, what happens is just one second. So what happens is that if you look at the trend over here, you would notice that HCl actually has the lowest boiling point and HI has the highest boiling point. But if you look at the polarity of the molecule, then HCl is the most polar molecule. It has the greatest difference in electronegativity. So it has pretty strong dipoles. Cl is very electronegative, H is very positive. But if you reach HI, the dipoles are kind of weaker. Just a second, it's not showing up. Just hold on one second. Okay, so this is what I'm talking about, HCl, HBr, and HI. In the case of HCl, the dipole is very strong. It's the H is very strongly positive, and the Cl has a very strong partial negative charge. But HI has a very weak dipole. It's not that positive, and I is not that partial negative. But even then, this one has the greater melting point. Why is that? The reason is that as you move down the group, you get this question a lot. There's going to be lesser electronegativity difference. So you have lesser and lesser electronegativity difference. And because of that, you have weaker dipoles down the group. Weaker permanent dipoles. So the boiling point should decrease actually if you go down the group, but it actually increases. And the reason it increases is that down the group, the size of the molecule increases. And remember, every molecule has van der Waals forces. So size of molecule increases, and you have more van der Waals forces. So you get more and more van der Waals forces, and because of greater van der Waals forces, what happens is you have so overall the melting and boiling points increase down the group. So this is what you're going to explain. That you're going to be asked that even though the permanent dipole strength is decreasing, but still the melting and boiling points are increasing, and the reason is that the permanent dipoles is definitely decreasing. And why is it? Because there's less electronegativity difference, but the size of the molecule increases and you have more and more van der Waals forces, uh, temporary dipole induced dipoles. So hence the overall effect is that the melting and boiling points they increase. Is this clear as well? Pazga, is this clear? Mohammed, Ethan, is this clear? Abba, is this clear?
Yeah.
Yes.
Acha, so the first one is so remember this. You'll get usually you get a pretty big question on this particular graph, explaining everything. 4 5 marks on this. So not 4 5 actually 4 would be the maximum marks. Why HF has a you have to explain this whole trend. Now coming to the electronegativity and the oxidizing ability, there are two things. One is if you look at fluorine, chlorine, bromine, and iodine, down the group electronegativity decreases, which means they don't like to gain electrons. Iodine doesn't like to gain electrons, and the reason for that is that iodine is too shielded. Its nucleus is already covered by so many electrons, so the nucleus is very shielded. It already has 53 electrons, and the nucleus is surrounded by electrons. Doesn't really like to gain electrons. Fluorine, on the other hand, a smaller atom, likes to gain electrons very strongly. Hence, fluorine is very electronegative, and the one who gains electrons is getting reduced. And the one who's getting reduced is basically acting as an oxidizing agent. So that means that when you move down the group, you get weaker oxidizing agents. Iodine is a terrible oxidizing agent. Iodine doesn't like to get reduced. Iodine doesn't like to gain electrons from someone else. Iodine doesn't like to oxidize someone else. So, I mean, this is already written. Smaller atoms are less shielded and attract electrons strongly. But when it comes to the negative ions, the halide, you're basically talking or referring to them as reducing agents because negative ions are not going to gain electrons, but instead they're going to lose electrons. So, who's going to lose electrons? Remember, bigger ions, they are more shielded and they lose electrons a lot more easily. So, if you have I minus 1, it's going to lose electrons very, very easily. F minus 1, because it's a smaller atom, doesn't really like to lose electrons. So this one is a very good reducing agent. Anything that's getting oxidized would be acting as a reducing agent. Anything that's losing electrons would be giving electrons to someone else, and it would be reducing the other substance. Hence, it's a good reducing agent. So the bottom two are pretty good reducing agents, especially the bottom two. These are these are very good reducing agents. Now, the next thing we're going to do is you get a lot of questions on this thing as well, and that's the reaction of halide ions with concentrated sulfuric acid. Now, the thing with concentrated sulfuric acid is that concentrated sulfuric acid H2SO4 is capable of doing two things. It's capable of acting as an acid, and if it's acting as an acid, it is a proton donor or produces H plus 1 ions. Or the second thing is it might be acting uh, as an oxidizing agent. So it's capable of doing two things. Now it can only act as an oxidizing agent. It can only act as an oxidizing agent if there's a reducing agent present. Remember, redox reactions happen. I mean, you need two things for a redox reaction. You need reduction and you need oxidation. If someone loses electrons, then someone else might be there that would be gaining electrons. Things can't happen on their own. ठीक है, an atom would not be just randomly losing electrons. Someone must be pulling electrons away from it. That's why it's losing it. So someone must be gaining electrons. So redox reactions are always reduction plus oxidation. Both things happen simultaneously. So if you want to talk about H2SO4 as an oxidizing agent, then H2SO4 can only act as an oxidizing agent if there is a reducing agent present. I said, so we just did this. We just did this. Okay, I told you that Br minus one and I minus one were pretty good reducing agents. So the thing happens, what happens is that if you take NaBr and you take this NaI, they both contain Br minus one and I minus one ions. Now what happens with them is that instead of a normal reaction, you start getting a redox reaction. So these two, they react because they have I minus one and Br minus one. So they're good reducing agents. Okay, and I'm going to explain this again. Why were they good reducing agents? Because big atoms, they like to lose electrons. I minus one would lose electrons very easily. Whereas F minus one and Cl minus one must be very terrible reducing agents. They don't like to lose electrons. So if we go back, focus on NaBr and NaI. They have, I mean, Na is irrelevant over here. It's just Br minus one and I minus one. They're very good reducing agents. So hence you get a redox reaction. Okay, is this clear?
Yes, sir.
Okay, so hence you get a redox reaction with H2SO4. And in that redox reaction, now I minus one was a much stronger reducing agent. So with I minus one, the sulfur is reduced a lot. I mean, you even get sulfur minus two. For example, if you look at all these molecules that are formed, sulfur, remember, in H2SO4 is plus 6. So in both these H2SO4, sulfur has an oxidation state of plus 6. And sulfur's oxidation would get reduced. It would form SO2, that's plus 4. It might form sulfur, which is 0. It might form H2S, where it's minus 2. So the oxidation state of sulfur is continuously decreasing in the reactions. Uh, Over here, SO2 is being formed, so that's plus 4. So I'm also going to add that I minus 1 is an even more powerful reducing agent compared to Br minus 1. I said compared to Br minus 1. Much more powerful reducing agent compared to Br minus 1. So you have two things happening, and what about Cl minus 1? Okay, this is what we talked about. Down the group, Br minus 1, I minus 1 became good reducing agent. Now, what happened with NaCl? Now, NaCl did not have a redox reaction. Why? Because it's not a reducing agent. So there is absolutely no redox reaction that's happening. No oxidation state is actually getting changed because Cl minus 1, it doesn't really like to lose electrons. And over here, you would also notice that Br minus 1 likes to lose electrons, so it would form bromine. Over here, iodine is getting formed. Uh, but Cl minus 1 doesn't like to lose electrons. So instead, you get a displacement reaction. And the H2SO4 is acting as an acid. So why do you get a displacement reaction? The reason you get a displacement reaction is that if you take a solution and you take a solution and you add Na plus and Cl minus 1 ions into it, and you at the same time add H2SO4, H plus 1 and SO4 minus 2 ions into it, what would eventually happen is that the H plus 1 and the Cl ions would get together and they would form HCl gas. and you would start seeing misty fumes of HCl gas being formed. So these H plus 1 and your Cl ions, they would be removed from the solution slowly, gradually. HCl gas would be formed and misty white fumes of HCl gas would be seen. So remember this reaction comes very often. NaCl is only going to have a displacement reaction, but if you add NaBr or NaI into H2SO4, you're going to get what you're going to get is a redox reaction. So why were we doing this reaction in the first place? This was a reaction in which hydrogen halides are produced. Like over here, you can see that HCl is getting produced. Okay, so this is one way of producing HCl. Take NaCl, add concentrated sulfuric acid, and you're going to get HCl gas. HBr and HI are also going to be produced in the same way, except that they further get involved in an oxidation and reduction reaction. And instead, all the HI gets converted into other products. So how do you, if you want to form HBr and if you want to form HI, what do you do? What you do is, TK, I'm going to write it here. To prevent a redox reaction, so what if, just one second, the board is not. So to prevent a redox reaction, what you do is, and to get and to obtain HBr and HI, what you instead do is so what you instead do is don't use sulfuric acid. Instead, use H3PO4. Okay, so instead use H3PO4 because H3PO4 is not an oxidizing agent. It's not an oxidizing agent, and you're not going to get a redox reaction. Okay, so stop using sulfuric acid because sulfuric acid would result in a redox reaction. So is this clear? Everyone, is this clear?
Yes, sir.
Okay, Ethan, Marble, is this clear?
Yes.
Yep.
Okay, then you have a disproportionation reaction that you have to remember, which is that that chlorine reacts with NaOH. This one over here is NaOH. One second, let me. So this one is NaOH. Chlorine reacts with NaOH to form sodium chlorate 1 and water and NaCl. And if the temperature is high, with hot NaOH, concentrated NaOH, it produces sodium chlorate 5, which has a different oxidation state. That's it. And this is known as a disproportionation reaction. You might be asked to label or balance some of these reactions. Bromine undergoes similar reactions as well. So similar reactions with bromine. And you might be asked to balance one of these equations. Now remember redox equations, how are they balanced? So for example, you have Cl2 reacting with NaOH, and it's forming NaCl plus NaClO3 plus H2O. So how do you actually balance these equations? A redox reaction. What you do is you figure out the oxidation reduction part. Cl is -1 over here, and you will notice Cl is +5. You can do the calculation. O is -2. So that's minus 2 into 3, that's 6. Na would be plus 1. So Cl must be plus 5. Now, the reason it's a disproportionation reaction is because the same element is getting reduced. So it's going to minus 1. And the same element is also getting oxidized. It's going to plus 5. So that means it's losing 5 electrons. And the same element is also gaining 1 electron. Now, in any redox reaction, you have to make the number of electrons gained and lost equal. To do that, you would have to multiply this by 5. So that means you should have 5 Cl minus 1 ions. So in total, you're going to have on the right side, you'll have 5 Cl ions and 1 Cl plus 5. So that means a total of 6 Cl atoms at the beginning. So that's how you balance redox equations, that the number of electrons gained and lost, they have to be made equal. And then you can balance the rest of the atoms the old way, which is that there are 6 Na. So it's 6 Na and there's going to be 3 H2Os. So just make sure the number of electrons gained and lost are equal. And what's a disproportionation reaction? In which the same element is oxidized and reduced at the same time. Then you have reactions with hydrogen. The fluorine and chlorine, they have vigorous reactions and the reactions slow down. With I2, the reaction is kind of slow and never reaches completion because HI decomposes very easily. It's a big bond. It's very unstable. The thermal stability decreases. So HI even decomposes at room temperature very, very easily. And the last part is, and remember about group 7, it's pretty much about all non-metals. Why is fluorine so reactive? Because fluorine is very electronegative, and it likes to gain electrons a lot. Why is iodine so unreactive? Because iodine doesn't really, its nucleus is so shielded that it doesn't really like to gain electrons from anyone, whether it's forming a covalent bond or an ionic bond. Its reactivity is going to be much, much lesser. The next part is the test of halide ions. Uh, the test of halide ions is, I mean, these are just the old tests. What you just have to remember carefully is that Cl minus 1 forms a white precipitate, a cream precipitate by Br minus 1, and a yellow precipitate by I minus 1. And you get a lot of questions on the solubility of the halide salts. Uh, the first one dissolves in dilute NH3. Br minus 1 doesn't dissolve in dilute NH3, it dissolves in very concentrated NH3, whereas I minus 1 is not soluble at all. And we've already discussed about the reactivity, so that's done as well. I think more reactive displaces a less reactive, so that's also obvious. Some uses of the halogens. Cl2 kills bacteria in water. Chlorine is used as a disinfectant. NaClO is used as a bleaching agent. You have CFCs and ozone destruction. I think we did talk about CFCs and ozone destruction in detail when we were doing organic chemistry. Now what we're going to try and do is we're going to try and solve questions on this. Okay, just one second. Let me open inorganic questions. Okay, so this one, starting with this one. Now the question, I said the first question. The question is, okay, so the question is that you're given, I mean, this one is we can actually ignore, it's more about Kp and Kc, so let's ignore this one for a second. Let's start with this one. What is the change in oxidation state of the element that is reduced? So you have to figure out which element is getting reduced. I is minus 1, and over here it's I2, so that's 0. So that's getting oxidized. So which element is getting reduced? H2SO4 is sulfur is +6, and over here sulfur is -2. So by how much? I think by 8. +6 to -2 is 8. The other part is which statement about astatine will be correct? It's right at the bottom of group 7. So it's going to be a dark colored solid at room temperature, because that's exactly what happens to the colors of the compounds. They become darker and darker as you move down the group. Colors become darker, they get darker. As it's more powerful. As the next one is, it is more powerful oxidizing agent than iodine. Is this statement true or false? Uh, Bigger atoms, astatine is bigger than iodine. They don't like to gain electrons. They are too shielded. So it's not going to be a powerful oxidizing agent. It's going to be a very weak oxidizing agent. And the hydride is thermally stable. It's not going to be stable because big atoms, they form weak bonds. So it's definitely not thermally stable. So if 2 is wrong, the third is also usually wrong. TK, is this clear, Ethan? Rida, Heba, is this clear?
Yeah.
Okay, this one is which of the halides, chloride, bromide, or iodide acts as a reducing agent when its sodium salt reacts with concentrated sulfuric acid? We just did this. Br minus one and I minus one were good. They were good reducing agents. So they would act as reducing agents, not Cl minus one. So which of the halide ions? At least one, that's true. At least two, that's also true. Not all three, because Cl minus one is not. It's not going to act as a reducing agent when it reacts with sulfuric acid. The first two will. As many compounds containing aerosols, which compound will cause the most ozone depletion? That is the one with Cl, because remember it's the first one, because it's the Cl bond that actually breaks in the UV light and produces these Cl radicals. And these Cl radicals, they go and they attack O3 to form. They would end up forming ClO plus O2 is going to be produced. And once that happens, the ClO then attacks another ozone molecule, ends up forming another Cl radical and produces two O2 molecules. As the next is, why do the halogen atoms become less volatile as group 7 is descended? Why do they become less volatile? Because remember, volatility depends not on the bond strength, it depends on the intermolecular force. And what's the intermolecular force for? I say it depends on the intermolecular force. And the intermolecular force is van der Waals forces. So we're talking about van der Waals forces. And what happens to the van der Waals forces when you descend the group? The van der Waals forces, they become weaker because they become stronger actually. Uh, why do they become stronger? Because the number of electrons are more. Okay, so you're not going to talk about the bond. You're going to talk about the intermolecular forces. This one is wrong because it's not becoming weaker; it's becoming stronger. Bigger molecules have more van der Waals forces. Okay, is this clear?
Yes, sir.
So, which statement about bromine is correct? Bromine is insoluble in non-polar solvents. Uh, Bromine vapor is more dense than air. That's which statement of bromine is correct? Will not vaporize and gaseous bromine is purple. So this is definitely correct because bromine is a pretty heavy molecule. It has an MR of 160. So all gases, they occupy the same volume. So having a really big mass is definitely going to make it heavy. The average MR of air is around 29 because it's mostly nitrogen. Nitrogen is 28, and the rest is oxygen, so that's 32. So if you average air out, that would be around 29. I said, what about the first statement? It's insoluble in non-polar solvents. Remember, non-polar things. Okay, let me write it on the board. So remember, non-polar things, they dissolve in non-polar solvents. So non-polar things dissolve in each other. Why do they dissolve? Because they neither attract nor repel. So if you mix them, they remain mixed. So if you have a non-polar solvent like CCl4 and you mix it with bromine and you stir it vigorously, now they don't have any reason to not mix. They're not attracting each other, neither they're repelling each other. So if you mix a bunch of CCl4 molecules with Br2 molecules, they would remain mixed. The problem would come if you mix bromine with a polar solvent. So if you have bromine and you decide to mix it with let's say water, what would happen in this case? If you decide to mix it with water, uh, the thing that's going to happen is that the water molecules are very polar. They have a very strong partial positive and partial negative charge, and they would attract each other very strongly. And the bromine molecules, because they're non-polar, they would be kicked out, on they'll be pushed aside, and they would be forced to form a separate layer. So same type of attractive forces always mix. So whether a molecule is non-polar, it's going to mix with non-polar. If a molecule is polar, it's going to mix with polar. But a polar thing and a non-polar thing, they're not going to mix together. Okay, is this clear as well?
Yes, sir.
Yeah.
I said now, so bromine is going to be very soluble in non-polar solvents because bromine is non-polar. Bromine will not vaporize significantly under normal conditions. Bromine usually does vaporize. It vaporizes a lot. I mean, lots of bromine vapors are formed. We can also have a look at the boiling point, which I think is below water. Okay, the boiling point is around 58. So water evaporates significantly. Bromine would be Alcohols evaporate significantly. Alcohols have a boiling point around 70. So bromine it's going to evaporate a lot more compared to the two. 59 degrees centigrade, that's very less. So significant evaporation would happen. And gaseous bromine is not purple, it's orange or brown or red brown. The next question is the same question. He's saying, which note correctly describes how sulfuric acid behaves in each of the reactions? So the first one is clear. Sodium chloride, it's only acting as an acid. There's no redox reaction that's happening. And the second one is with conscious. He's asking, what would it behave like with sodium iodide as a strong acid only, or as a strong acid and an oxidizing agent? So it's going to be this one. We just did this. That if you look at the reactions, so what you're going to notice is that NaI first has a displacement reaction with H2SO4 to form HI, and then the redox reaction starts. So it is definitely behaving as a reducing agent. ठीक है ऐसा. अच्छा, next thing is Here's the question. What happens when chlorine is bubbled through aqueous potassium iodide? Now you know that chlorine is more reactive. So what would it do? It's going to displace, it's going to form KCl, and I2 is going to be displaced. So what happens when chlorine chloride? So which one is the correct answer? Chlorine is oxidized to chloride ions. That's incorrect. Although it is changing into chloride ions, it is changing into Cl minus one. But changing into Cl minus one is reduction, not oxidation. So this word is incorrect. The second one is iodide ions are oxidized to iodine. That is correct. C is correct. Because I minus one changing into I zero, that is correct. That's oxidation. So C is correct. Iodide ions are oxidized to iodine. Next is the ability of an atom to form a in a covalent bond to attract electrons to itself is called its electronegativity. The greater the difference between the electronegativities of the two atoms in the bond, the more polar. So he's asking which will form the most polar bond. Can anyone answer which one is the most polar?
D. Fluorine and iodine.
C.
The fluorine and iodine, fluorine top पे, and iodine is at the bottom. So the difference,
That's right.
you get the difference is huge, and the electrons would all be pulled towards fluorine, which is why it's going to be very partial negative, and iodine is going to be very partial positive. The next one is which statement describes the halogens chlorine, bromine, and iodine? Their bond energies decrease with increasing proton number. That is correct. Why is that correct? Because bigger the atom, the bonds would be weaker. So the bond energy would decrease. Bigger atoms, they form weaker bonds. The rest are therefore all incorrect. They are all colored gases. The, the bond energies decrease with increasing. I mean, I think the first one is correct. They're all colored gases at room temperature. So why is this incorrect?
Because chlorine is not colored.
The chlorine is greenish yellow.
They're not all gases. Some of them are solids.
Exactly, because they're not all gases. Only chlorine is a gas, bromine is a liquid, iodine is a solid. So then the ionization increase with increasing proton number. That's incorrect because bigger atoms they lose electrons easily, and they're all good reducing agents. The term reducing agent would not be applied to them. The term reducing agent, is used for the ions, not for the elements. Remember this. Remember this. TK. When you're describing the element, you use the term oxidizing agents. So if you talk about fluorine, chlorine, or bromine, you're basically talking about them as oxidizing agents because they're going to gain electrons. The term reducing agents is for the ions. You wouldn't call this fluorine. This is fluoride. This is chloride. This is bromide, and this is iodide. So, what's incorrect over here is that this term is not used for the element. Next one is that silver nitrate is added to an aqueous solution, and he says that it contains sodium iodide, I minus one ions. So concentrated ammonia is added. What would be the observation? Now with I minus one, a precipitate forms, and the precipitate is going to remain. It's going to be D, because if you look at the test for the ions, so if you look at the test of the ions, you would notice that I minus one precipitates are not soluble in NH3. Okay, they're absolutely not soluble, so nothing would happen to them. Let's move to the next one. The chlorine free radical takes part in the destruction of ozone. Which statement was this free radical are correct? It is formed by the heterolytic fission of the covalent bond in the chlorine containing molecule, which is true that if you have a CFC Radicals are always, remember in organic chemistry, radicals are always produced when you have, this statement is actually incorrect. Radicals are always produced when you have homolytic fission, when the bond breaks equally and the Cl leaves with one electron. So if one is incorrect, second and third are correct. It has a single unpaired electron, which is true because chlorine has all its orbitals completely paired. It has the same electron arrangement as the chlorine atom, which is also true. I mean, chlorine radical and the chlorine atom are basically the same thing. So which statement with the reaction of which statement of the reaction of solid bromide with concentrated sulfuric acid are correct? It's the same. You're going to have. I mean, we can have a look at the reaction that you're going to get HBr first. NaBr with H2SO4, you're going to get HBr, and the HBr would be oxidized by H2SO4, which is going to act as an oxidizing agent to form bromine and SO2. So that's the reaction. So sulfur dioxide is formed, but again, what's wrong here is that it's not oxidized; it's actually reduced because in H2SO4 sulfur is +6. In SO2 sulfur is +4. So if 2 is correct, 3 is also correct. Bromide ions are reduced; they're not reduced; they're actually oxidized. Bromine is forming, but it's getting oxidized. So only the first one is the correct option. Okay, is this clear?
Yes, sir.
Yes.
So here, let's do one last question, which is this one. Which graph correctly describes a trend found in the halogen group? The boiling points, they don't decrease. Do they decrease? They increase down the group because van der Waals forces. I2 is going to have more van der Waals forces. A bond length, it does not decrease; it increases. You have bigger atoms, you have bigger bonds. B is the correct one. Van der Waals forces, they keep on increasing. Bigger molecules have more van der Waals forces. So B would be the correct option. TK, is this clear?
Sir, what do they mean by bond length?
The bond length is bigger atoms, they form bigger bonds. Like for example, if you're talking about fluorine, right? So fluorine has 2pZ1 overlapping with let's say hydrogen.
Okay, I get it.
It's a small orbital, right? And the small tiny orbitals, they are overlapping. So the electron density would be in the middle, but they would be very close to each other, right? So if you have a big atom, then the bond length is greater. So here, let's continue with this next class then.
Still Allah Hafiz, Shahid.
Okay.
Allah Hafiz.
Take care. Bye bye.
Thank you.